Modern large language models have sophisticated reasoning capabilities, yet they remain dormant by default. They wait for an external trigger before executing a single calculation. This reactive state traps the AI in a prompt response cycle. It exists within a cloud environment, processing a human query and returning to a stateless rest. For enterprise operations, this model is slow. Private systems require constant management, and a framework that waits for a human to initiate every step creates an immediate operational bottleneck. Relying on human prompts introduces a specific vulnerability: contextual drift. This timeline tracks a system failure against a human response. When a server error occurs on the left, the delay before a human notices the alert creates a gap. By the time someone prompts an AI for help, the environment has already shifted. During that window, traffic may have rerouted or logs could have been overwritten. The AI receives a snapshot of a state that no longer exists, leading to troubleshooting steps that don't match the current reality. Managing live infrastructure through disconnected chat interfaces results in high latency and security risks. The system needs the ability to observe and respond the moment a deviation occurs. OpenClaw shifts the AI from a stateless chatbot to an event-driven operator. It accomplishes this by inverting the standard polling loop. Instead of waiting for a user to start a sequence, the system monitors its own environment. OpenClaw ingests data from asynchronous sources, like standard webhooks, live RSS feeds, and raw system logs as they happen. This constant ingestion provides the AI with a near real-time view of system health. It identifies errors and initiates workflows without requiring a human to type the first word. To give an AI agency over a private system safely, OpenClaw uses a 3-layer architecture. The gateway acts as the entry point. It takes disparate, messy event streams and translates them into a standardized format that the reasoning engine can interpret. The second layer is the core. This decision-making hub compares incoming data against the system's ongoing state and long-term memory. The core uses dual-path routing, directing routine data to local models for speed while sending complex planning to cloud APIs. The third layer is the Skill Registry. This sandboxed environment maps the AI's intent to modular, executable code blocks. Security uses a vault injection pattern. Task credentials are provided at the exact moment of execution and are purged the millisecond it completes. This architecture keeps the AI's reasoning engine isolated from the execution environment, preventing unauthorized commands from reaching the host system. To stay updated on how these autonomous agents are changing technical infrastructure, subscribe to The Explainer. Granting an agent the power to execute code raises a safety concern. How does the system handle an ambiguous log or a high-risk command? OpenClaw manages this through a human-in-the-loop protocol for any action defined as a critical failure or a restricted command. If the AI identifies a need to force push a repository or modify a core directory, it pauses and sends an alert. You receive a notification with the full context of the request and 3 choices: approve, reject, or modify. This framework automates routine triage while ensuring that an operator remains the final authority for every high-stakes executive decision. This architecture enables existing background programs to utilize the AI's logical inference. Standard IT automation relies on scripts that follow rigid rules. If a service crashes, a script might simply restart it without identifying why the failure happened. OpenClaw follows a different sequence. It reads the pre-crash logs, analyzes the stack trace to determine the cause, and documents the error in a ticketing system before it ever attempts a restart. By integrating language models directly into the local environment, OpenClaw creates a self-documenting immune system that manages the enterprise autonomously.